talking about uncertainty quantification in inverse problems, Aretha's now going to give us an overview of that problem. Okay, Aretha, thank you.
Okay. Thanks, Peter. So, I'm going to give a talk on uncertainty quantification in inverse problems. So, inverse problems was one of the, as Peter said, one of the topics that we had for the program and for one of the workshops. And so, the outline of my talk is the following. So, I'm going to first set up the problem. So, I'm going to talk about inverse problems, what they are, and how we solve them. So inverse problems is maybe a term that's more from the applied mathematics community. So the particular inverse problem that I'm going to show you is also known as a model calibration problem or a parameter identification problem. Then the plan for the talk is to give you some idea of the main topics that we discussed, or the main challenges that we discussed in parts of the program. So one of the challenges I'm going to discuss in detail is about surrogate models. So we already heard a talk about surrogate models this morning by Max. And I'm going to talk about how we can use these surrogate models specifically in the context of inverse problems. Then another topic which we had a lot of discussion about is model discrepancy, also known as model inadequacy or model bias. So this is where you have a discrepancy between the real-world system and the mathematical model that you're using, and you somehow want to incorporate that into your procedures. And then I'm going to have one slide of a couple of other things that we discussed and how they relate to the other talks that we've heard today. Okay. So I realize there's a lot of people here from very different communities, so if anything in my talk is unclear at any point, then please feel free to interrupt and ask for clarification on that. Okay. So as I said, I'm going to start by setting up inverse problems, so what kind of problems we're interested in solving here. So an inverse problem is really just a problem that is concerned with determining causal factors from observed results. Okay? So we put it kind of in a mathematical formulation. We assume that we have a mathematical model of some process that we're interested in, and what we want to do is we want to determine the model inputs based on data that we have of observable model outputs. So we have some mathematical model, maps the inputs to the outputs. What we really want to know is the value of the inputs, but the only thing that we can observe are the values of the outputs. Okay, so we can't observe the inputs directly, we can only observe the outputs, and so we want to use data about the model outputs to learn what the model inputs were. Okay. So maybe that's a bit more clear when I show you these examples. So these inverse problems appear in very many different application areas. I've given you two specific examples here to illustrate what I mean by what I just said. Okay. So the first example is an example in seismology, where you want to determine an earthquake's epicenter using observations of the seismic waves on the Earth's surface. Okay, so when an earthquake appears, it starts somewhere below the Earth's surface. You can't measure anything there. What you can measure is once the seismic waves have propagated through the Earth to the surface, and then at the surface you can take measurements. So you have measurements of that, of the seismic waves at the Earth's surface, and from that you want to infer where the earthquake started, so the earthquake's epicenter. Okay. Another example here is in non-destructive testing. So in non-destructive testing, you have a big concrete structure where you want to infer whether there's a flaw or a crack inside, and obviously you want to do that without having to take the whole structure apart, so you don't want to have to take this whole building apart, for example, in order to see if there's a crack in the wall or something like that. Okay? So the way that this works is you detect flaws or cracks within a concrete structure from acoustic or electromagnetic measurements at its surface. So for example, for the wall, you would take acoustic or electromagnetic waves, you would send them from one end to the other. So you have the sender at one end, the receiver at the other end, and then you use the measurements that you get from there to infer what the wall looks like on the inside, if there's a flaw or a crack. Okay? So both of these examples fit into this framework here. So the mathematical model that I'm talking about is frequently given by a differential equation. So for example, here we have the seismic wave equation, and here we have the acoustic or the electromagnetic wave equation. And the things that we are going to view as inputs, so the type of things that we're interested in learning or estimating, are things like the initial conditions, boundary conditions, or the coefficients. Yeah, so in this example here, we want to learn the earthquake's epicenter that is related to the initial condition of the seismic wave equation, where the wave starts. In this example here, we actually want to infer the properties of the medium. So again, in the wall example, we want to infer the properties of the wall, so material properties of the wall, and that's actually related to the coefficient that you have in these PDEs here. Okay? So those are going to be our inputs, and the outputs are going to be just observables of the solution. Yeah? So here you have the seismic waves at the Earth's surface, which means that you have the seismic waves at a certain point in time and space. So that is going to be the solution of the seismic wave equation, and observables, which are just evaluations at a certain point in time and space. Okay? So these are the type of models that we're interested in. I'm now going to formulate that in a more mathematical formulation. Okay? So we have our mathematical model of some process that we're interested in. So for example, in the seismology example, in the earthquake example, that's the propagation of waves in the Earth's surface. And I'm going to denote this mathematical model by G. Okay? So it doesn't really matter what exactly this G is. In most applications that I'm talking about, it's typically nonlinear, and that's really, well, you don't even need to know that, but that's really all you need to know. And then you can write the inverse problem in the following way. Okay? So we assume that we have some observational data. Okay? So this is real-world data that we have collected. I'm going to call that Y, and I'm going to assume that that we have finite dimensional data, so there's a finite number of data points, and I'm going to assume that we have dy data points Y. Okay? And we want to use these observed data Y to determine an unknown model parameter, which I'm going to denote by U. Okay? And in particular, the data Y has this form here. Okay? So that's exactly what I explained on the previous slide. The data Y that we have is not directly related to the model input U, but it's related to the model output. So the Y is related to G of U, and then we assume that we typically in applications you also have some noise in here. So this eta here represents observational noise. That is, for example, due to measurement errors. So the instruments that you're using to collect your data Y could not be calibrated exactly, or they could also only give you finite accuracy, so they could only give you, say, 3 significant digits or something like that. Okay. For the parameters U, so the parameters U are now what we want to find or what we want to learn. I'm going to assume that we have a finite number of those as well. So we just have du parameters U, and for simplicity, I'm going to assume that they take values in a compact set, so they're just in a closed and bounded set. And this is just to make the theory easier, so you can also work in unbounded sets. So if you have a bounded set, then everything is a bit more easy. Okay? You can also do, in general, you can work with parameters U, which are functions. So here I'm assuming that we just have a finite number of scalar parameters U. You can also do the same thing when the U is actually a function, so when it's an infinite dimensional object, but I'm not going to talk about that today. Okay. So we have our data Y, which is what we have observed, and we want to find the model parameters U, which gave rise to this particular value Y. Okay? So from this equation here, you know Y, you want to find U, so essentially you want to invert your mathematical model G, and that's also where the name inverse problems comes from. But most of the time, simply inverting G is not an option. So one problem is that we don't know the value of the observational noise. So even if we could invert G, because we don't know the value of the noise, we only know Y, we can't just apply G inverse. Okay? The second problem is that this problem is typically what's known as an ill-posed and an ill-conditioned problem. So ill-posed means that there's not a unique solution. Okay, so for example, there could be several values of the parameter U which give rise to very close or the same value of Y. Okay. And then ill-conditioned means that this problem, even if it is a well-posed problem, so even if there is a unique solution, it's typically ill-conditioned in the sense that if you then try and compute the solution to this problem on the computer, because it's so ill-conditioned, if you implement it on a computer, you'll actually not get a sensible answer. Okay? So it's ill-conditioned, you don't have stability, so it's a very unstable problem, and the rounding errors on the computer will mean that your answer that you compute is actually complete rubbish. Okay. So you can't really just invert G, so what we typically do in inverse problems is that we work in a statistical framework. Okay? So we work in a statistical framework, and what we want to do is we want to find a probability distribution on our parameters u given the data y. Okay? So that's what we're now going to do. So we're going to do a statistical approach, in particular it's a Bayesian statistical approach. All this means is that we're now treating our unknown parameter u that we want to find and the observed data y and the observational noise eta as random variables. Okay. Then the first thing that you do is you choose what is known as a prior distribution or a prior density on your unknown u. So this is just a PDF, the probability density function, which I'm going to denote by pi0 on your parameter u. The way that you choose this distribution depends very much on the application that you're working on. So you choose it to incorporate all the information that you have on your unknown u prior to observing the data y. So that's where the prior comes from. So it incorporates things like positivity, if you know that your u is always positive, or you might have some other geometrical constraints, or things like that. Okay. Then the next thing that you do is you look at the likelihood of the data. Okay. So what we mean by the likelihood of the data is you calculate the probability of observing a given value y given u. Okay. So given the value of the parameter u, what is the probability that we're actually observing our data y? The way that you compute this is by looking at the data generating model, the measurement model. So we assume that the y was the model output t of u plus some observational noise eta, and now we're assuming that the eta is a realization of a normal random variable. So it's just a random variable. Here I'm assuming mean 0. You can also do non-zero mean here. And then you have some covariance matrix gamma. Okay. So then if you look at the random variable, that is the data y given u. Okay. So if in this equation here, if you fix u, then this is just a constant, and so you just have a normal random variable plus a constant. So that's again another normal random variable, where the constant is just added onto the mean. So the y given u is just this multivariate normal distribution, and then you can write down this density, the PDF of y given u, which is just the PDF of this multivariate normal, and that is just exactly this term here. Okay, so that's just the density. This normal, we have hidden the constant that goes in front because it's not important for our purposes. Okay. Then we get what is known as the posterior. Okay, so if you're familiar with Bayes' theorem, this posterior distribution comes directly from Bayes' theorem. Bayes' theorem just tells you that the probability of u given y is proportional to the probability of y given u times the probability of u. So that is exactly where this here comes from. So the posterior density, which is denoted by pi y, we have on the left-hand side here. And from Bayes' theorem, we know that it is the probability on u. So that is the prior that we have here. Then we have the PDF of y given u, which is this term here. And then we have this normalizing constant here as well. So we have the z here, and that is just a normalizing constant. So we want to ensure that we have a probability distribution. You know, probabilities always take values between 0 and 1, and so we have to normalize this to ensure that we are between 0 and 1. Okay? So you just get this formula here, and that is what we call the solution to the Bayesian inverse problem. Okay? So in the inverse problem, we were given the data y, we wanted to find u, and that's exactly what we've done. We now have a probability distribution on u given y, and it takes this form here. Okay? Okay. So this workshop is all about uncertainty of quantification, and in this statistical framework that I showed you, we actually do get uncertainty quantification in u given y. Okay? And that's because the way we solved it, we were solving it using a statistical approach, so we don't just get one estimate or one value for the unknown u, we do get a whole probability distribution on u. Okay? So this probability distribution is going to tell us on how certain we are in the estimate of u. So for example, we could have a PDF pi y. If it is very peaked, so if it's very narrow, then we know we're quite certain about the value of u. If it is very flat, then we're not very certain about u. If this distribution is unimodal, then there's really only one value of u that gives rise to the data y. If it is bimodal, then we have two possibilities for u, and so on. Okay? So this approach allows for uncertainty quantification. Okay. Then the goal in the simulations is usually one of these two. Okay? So usually you want to produce some samples from the posterior, so you want to draw possible values of your parameter u, given the data y. So this is typically done using things like Markov chain Monte Carlo methods or Metropolis-Hastings methods, which people might be familiar with. Another thing that you might want to do is compute what is known as the maximum a posteriori or MAP estimate. So this is just the point that is most likely. Okay, that's the point that's most likely under your posterior distribution, so it's defined as the one that maximizes the posterior density. Okay. Now in the case of models G, which we're interested in, which are given by differential equations, there are two important challenges. Well, there's a lot of challenges, but there's two which I want to concentrate on in this talk here. So one is that the computation of the log likelihood phi is typically very costly. Okay, so let me just go back to the definition of the posterior. We have here our prior and then the data likelihood. Okay, so I've introduced this phi here, which is just the data likelihood here. So if we go back to the definition of phi, that is the mismatch or the difference between the observed data y and then the predicted model response for a certain value of u. Okay? And so to evaluate phi, you have to evaluate g. So if you want to compute the data likelihood or the log likelihood phi, then you have to solve your model equations g. And to solve the model equations g, you have to solve this differential equation, which is typically very expensive. Okay? So computing the data likelihood is very costly, and so what you can do is you use these surrogate models to reduce the cost of evaluating phi. So the definition that I'm using for surrogate models here is very close to what Max was using earlier this morning. So by surrogate models, I just mean any function that approximates the true function phi that you're interested in, but which is a lot cheaper to compute. Okay? So you might also know these as emulators or reduced order models, depending on which community you're from. And the question that you then might ask is, well, if I'm approximating my model G by a surrogate model, how does that actually influence the posterior that I get? So how does that influence my estimate of u given y? Okay, so that's one thing I'm going to talk about. And then another important aspect is what we call as model discrepancy or model bias. So typically the data y is usually real world data, and so there's going to be this discrepancy between the mathematical model G that we have, our differential equation model, and the real world, and then there's a question of how you can incorporate this into the analysis. Okay, so I'm going to start by discussing the use of surrogate models. Okay, so this is just the definition of the posterior density again. Okay, so this is the posterior, this is the distribution on u that we're after. It's given in this form here in terms of the prior and the data likelihood. And all we're going to do now is we're going to approximate either the mathematical model G or directly the likelihood phi or the log likelihood phi by a surrogate model. Okay, I'm just going to denote that by phi n. And then all we're going to do is instead of the true data likelihood phi, we're going to have the approximate likelihood phi n. Okay? And then the question that we want to answer is how close is this distribution to that distribution. Okay. So, as I said, the definition I'm using for surrogate model is very loose, so it's any model that you like that approximates your true model at a much cheaper cost. So we already heard a lot of examples earlier this morning by Max. So he, for example, discussed interpolation methods, so interpolation with the Lagrange interpolation or radial basis function interpolation. He also discussed regression type methods, such as least squares, and then you have these reduced order models, such as proper orthogonal decomposition or reduced basis methods. Okay? And all of these methods are what I would call here deterministic methods. Okay? So what I mean by deterministic here is that when you given a function, if I give you a function phi and you produce any of these approximations, then they are completely determined. Okay, so if you do the process once, you get an answer. If you do the process again, you get exactly the same answer. And so there's really only one interpolant. If you're doing Lagrange interpolation, then there's a unique one interpolant that you get out. Okay. There's other methods which I'm going to call stochastic, and in that sense, stochastic methods here for me means that there is some sort of randomness in the construction of your surrogate model. So if you run the algorithm to construct the surrogate model once, you get one answer. If you run it again, you will get a different answer. Okay, so there's some randomness in the construction. Typical examples are, for example, here in randomized projection methods. So if you have either an observation space, so this space where the observations y live, or a parameter space where the parameter u lives, which is very high dimensional, then frequently what you do is you project it onto a lower dimensional subspace, or you try and find active dimensions, and that is quite frequently done in a random way, because projections onto random subspaces have very nice properties, and so because you're doing this projection in a random way, there is some randomness in the construction of the surrogate model. And a very big class of other examples is, for of course, if you're doing a statistical method or statistical surrogate model, such as, for example, Gaussian process emulators, then you automatically also get a random surrogate model phi n. Okay, so if we look back at the definition of our approximate posterior, okay, so this is just the posterior density, our estimate of u given y, with the true mathematical model replaced by a surrogate. That is this model here. If this phi n, if it's deterministic, then this here is absolutely fine. If it's stochastic, then you here actually you have a stochastic object here. So in that case, you have to think a bit about how you actually want to define the PDF or the posterior, how you want to define the posterior PDF. If you just do the same and you just plug it in here, so with the omega here, I'm trying to denote the randomness. So the omega is an element in a probability space, or a random parameter. If you do that, then the PDF that you get is also random. So for different realizations of your stochastic surrogate model, you're going to get different realizations of the approximate posterior, which makes sense. So then you have a random approximation to the posterior. You can get rid of this randomness either by fixing omega, so you fix and you just take one specific realization of your random surrogate model. Say when you're doing the projection onto random low-dimensional subspaces, you just choose one realization of that projection, you project onto that subspace, and then you're dealing with that. Okay, so that's what this corresponds to. Then you get one approximation to your posterior. Or you can do what we call the marginal approximation. In that case, you're actually integrating out the randomness. Okay? So you're constructing your random surrogate model many times, and then you average over the different realizations of the surrogate model. Okay. Now this was quite technical. I hope it wasn't too technical, but this is just to give you an idea. And then, as I said, what we're really interested in is the difference between the true posterior density, so the true distribution on u given y, and then the approximate distribution that we get on u given y if we use a surrogate model to approximate the true mathematical model. And what we can show is that we actually get what we call convergence. So So we can show that the approximate posterior densities constructed with the surrogate models actually converge to our true posterior density, as the approximation phi n that we're using for the log likelihood converges to the true log likelihood phi. Okay? So what this means is that this is a justification for the use of surrogate models in Bayesian inverse problems. This tells you that it is okay to use the surrogate model to approximate the true model, and it shows that the error that you're committing, so the difference that you get in your distribution on u given y, is small as long as your approximate surrogate model is close to the true model. Okay? So as long as your surrogate model is close enough to the true mathematical model, you get a posterior that is close to the true posterior. Okay? So if you're interested in more details, so there's a couple of references here where they show this kind of result here. Okay. So that's what I wanted to say about surrogate models. So of course there's the theory that is developed in these papers here is very general, so you can really use any surrogate model that you like. So you can use anything that you saw in Max's talk earlier today. There's also a couple of other examples here. So in the talk I've tried to include a lot of references, so for those of you who are interested in trying these methods out, I've tried to include at least one reference for every method that I talk about, and of course these lists of references are not going to be exhaustive, so I apologize if I left out anything important. Okay, so so these are just some examples. So Gaussian process emulators, that's something that's very well known in the statistical community. You can use that. Then there's these dimension reduction methods. You can also fit that into this framework. So you can do dimension reduction in the parameter space, the dimension reduction in U. We had a talk by Paul Constantine about that in the 4th workshop. You can also do dimension reduction in the observation space, so dimension reduction in Y, used in the context of big data. We had a talk by Tan Bui Tan about that in the 3rd workshop. Then there's these projection-based reduced order models. Then there's things like generalized polynomial chaos and sparse grid collocation, which are more methods from the applied mathematics community. Okay. So you can use any of those really. Which ones you use, again, depends on your application. So different methods are appropriate for different applications. One important distinction, which we've discussed a lot about in the program, and which was also discussed in the talks earlier today, is whether the model G that you're given is given to you as a black box, or whether you actually know what the equations for G are. Okay? So if your model G is given to you as a black box, then all you can do is evaluate G. You don't have any idea of the structure of G or anything like that. All you can do is evaluate it, and then you're a bit more restricted in the methods that you can use. But for example, things like Gaussian process emulators, dimension reduction, reduced order models, those methods mostly still work fine. Whereas these kind of methods like generalized polynomial chaos and sparse grid collocation from the applied mathematics community, they do make more use of the explicit equations that you have for G, so you would have to know exactly what the PDE is that you're solving. Okay, so that's the use of surrogate models. So as I said, another important aspect which I wanted to talk about is model discrepancy. So model discrepancy, so it's also known as model inadequacy or model bias. It's just about the difference between your model and the real world. So far, what we assumed is that our observational data Y is of this form here. So the Y is equal to some model G applied to our parameters U plus noise eta. And here G was our mathematical model. This is our differential equation, the seismic wave equation, or the electric magnetic wave equation, and we assume that that is the process which generates the data Y. Okay? So in that sense, the error term eta that we have here, it includes 2 sources of error, okay? Maybe more as well, but it definitely includes these 2 sources of error. One is measurement error, which I already discussed earlier. Okay? So this is, for example, due to your instruments only having a finite accuracy, or the instruments that you're using to observe to get the observations y are not calibrated accurately. And then the second term that it includes is this model discrepancy that is due to the difference between our model G and then the real world. Okay? So the y, the data y that we have, that we're given, is really from the real world, it's real data, so there's this difference between that and our model G. Okay. Now, a typical assumption which you see quite often is that you, which you also saw in the talk earlier, that this error term eta is normally distributed. So it has, it's a normal, multivariate normal with some mean m and some covariance gamma. Okay? So one reason that this assumption is frequently used is that everything is well defined in that case. Okay? So the setup of the Bayesian inverse problem that I showed you in the beginning is well defined. Everything that I said still goes through. Okay? Another thing is that quite frequently you don't really know what this noise is. Okay? So you might know what the mean is, you might know what the covariance is, and if the mean and the covariance are all you know, then the normal distribution is the a natural distribution to choose. Okay? So if you don't have any more information on higher order moments or anything, then the normal is quite the normal distribution is quite a natural choice here. Okay? The question is then, how do we actually choose the m and how do we actually choose the gamma? Okay? So the eta here is supposed to incorporate these two errors. So how would we actually choose the m and the gamma such that it does actually represent those two errors? Okay? So that's actually a very difficult question. So in particular for this part here about the model discrepancy, for the measurement error, you can quite often get away with just assuming that it's IID, it's a bit easier. For the model discrepancy, it's actually a lot more structured term, and so it's actually quite difficult to define a distribution on it. Yeah? So the model discrepancy, it's supposed to model the difference between your mathematical model and the real world. Okay? So how do you put a distribution on that? In some cases, you actually do have some structural information about the model discrepancy. So you do actually have some information about the difference between the real world and the mathematical model you're using. So that's, for example, comes in when you have simplified physics. Okay, so you might, in very complicated, in complex systems, like we heard today, in complex systems, you quite frequently have a lot of very different processes that influence the thing that you're trying to model. And then if there's a process which is kind of less important than another one, then maybe you ignore that one because you know that that one's less important. It doesn't contribute as much to the process that you're interested in. And so you kind of have simplified physics where you know that you have ignored certain physical processes just because they're not that important. So in that case, you know which processes you have ignored. So say you've ignored some higher order terms. And so then you do actually have some idea about what the model discrepancy is. Okay? But a lot of the time, you don't know what it is, and you have to, and you don't even know the structure of it, and you have to estimate it, and this is actually a really hard problem. Okay? So one of the hard problems is that you have identifiability issues. Okay? So what that means, identifiability issues, means that even if you have an infinite amount of information, there's no method for learning the model discrepancy. Okay, so the model discrepancies are not identifiable. You cannot develop a method that would give you an estimate for it, even if you have an infinite amount of information. And the reason for that is, if you look at this equation here, so you've got your model G, and then you've got the eta. So here, what you're observing y, and the y is the sum of the model plus the eta, which is the sum of the measurement error and the model discrepancy. So the only thing that you're observing is the sum of the model error, and the measurement error. Okay? And when you're only observing the sum of three things, you won't be able to identify them all individually. Okay? So if you think about it, if you're just observing two real numbers, you know the sum of them is 2. You don't know if they're both equal to 1, or if one of them is 2 and one of them is 0, or the other way around. And so there's this identifiability issue that because you're only observing the sum of these three terms, you can't really identify it, identify the terms individually. Okay, so then there's something that you can do. There's some recent progress in, for example, this paper here by Plumley, published last year. Okay, and the key idea is the following. So the model discrepancy, you wanted to model the difference between the real world and your model. Okay? If you know what physics you have left out, then you know you have an idea of what that difference is. But in general, if you only know what your mathematical model is, then trying to estimate the difference between the mathematical model and the real world is very difficult. Okay? So the idea in this Plumley paper is that you kind of choose the model discrepancy to be orthogonal to your model. Okay? So what I mean by that is the following. So you have your mathematical model, and then the model discrepancy, what you wanted to do is capture everything that the mathematical model doesn't. Okay? So that's exactly, there is a way that you can do that. Okay? So you just need to know what your model is, and then you can do some tricks to define the kind of space or the part of the real world that the model doesn't capture. Okay? The way that you do this is the following. Okay? So we're going to define the model discrepancy as the difference between our real world data y, okay, and then and the best model g of u star. Okay, so the model discrepancy is going to be the difference between y and then the best possible model that we can find for y in terms of g. Okay, so in general, the g of u, it's a parametric model, so we can choose different values of u, and the u star is defined as the one which gives the best model. Okay, so you define the u star in terms of minimizing a loss function between the real world and your model. Okay, so essentially the u star minimizes the difference between y and g of u. So it is the best one in that sense that the u star gives you the best possible model. Okay, and then using that definition that it is the u star is the best possible model that you can have, then you can use that explicitly to derive a distribution on the model discrepancy. Okay, so you can use that to explicitly derive a distribution on the model discrepancy eta 2. And don't really want to go into too much detail here, but you can show that the distribution that you get on eta 2 using this procedure involves the gradient, so the first derivative of your computer model. Okay? And the model discrepancy is orthogonal to the gradient of the model. Okay? So what that means is the following. Okay? So you can imagine that you have your mathematical model G. Okay? So you have G of u. And then the gradient of the mathematical model, so the gradient is going to tell you in which direction the model changes. Okay? So if I vary u, then g of u is going to go in the direction of the gradient. Okay? So if I vary u, then if the gradient points in this direction, then it's going to, as I vary u, g of u is going to vary along here. Okay? So this is kind of the space that I get with all my different models g, and so the difference between g and the real world is what's not captured by this direction. Okay, so that's why you want to choose the model discrepancy going in this direction, kind of, so it's orthogonal to the gradient, so it's at a 90-degree angle, so it's kind of going in exactly the direction that's not captured by your model G. Okay. So that was a bit about model discrepancy. It's a very difficult problem, as I said, and there has been some progress on that. And I just wanted to finish with a couple of other questions that we have discussed during the program and have also been discussed earlier today. So one question is how we should actually collect the data y. Okay, so that was Dave Wood's talk earlier today. It's related to optimal experimental design. In many applications, you can actually choose how you collect your data y. So if it would involve setting up some sensors or something like that, then you can choose how to do that. And there's this whole area of optimal experimental design about that. Here's just a couple of more references if you're working. So if we're working with these differential equation-based models, then these models are very expensive to deal with, and sometimes even if you use surrogate models, then these standard methods such as Markov chain Monte Carlo, Metropolis Hastings are still too expensive, and that's because the probability distribution, the probability distribution on U given Y, so a posterior density, is typically a very complicated object. Okay, so the posterior on U given Y, it can be very concentrated, so it can be very peaked and concentrated in a very small space. It can have very weird geometric configurations in it, so sometimes it's a bit difficult to get these to work. There's essentially two ways that you can get around that problem, that the posterior is a very complicated distribution, so you can, one thing is doing a Laplace approximation, which means that you're approximating your posterior by a simpler distribution, particularly approximating the posterior by just a Gaussian, by just a normal distribution. You can do that. And then there's also kind of ad hoc methods, which, as opposed to Metropolis Hastings and Markov chain Monte Carlo methods, they don't really sample from the true posterior, but they sample from a distribution that is close to it. And then these methods can be faster to implement, such as the ensemble Kalman filter. And then the last thing I wanted to point to the last talk today, so Richard Wilkinson's talk in just a minute, which is about multi-level and multi-fidelity methods. So when you're using these surrogate models that I talked about earlier, you don't just have one surrogate model, but you can construct a whole hierarchy of surrogate models, and you can actually use that very efficiently to reduce the computational cost even further. And then in particular, I wanted to point out this multi-level community web page, which is a page maintained by Mike Giles at Oxford, which has all the references from the applied mathematics community in the multi-level community. Okay. So this is being recorded, so I'm just going to flick through the references so that they are on the video. And thank you very much.
Thank you very much. Time for a few questions.
Aretha, really nice talk. Thank you. The question I wanted to ask is, what's been your experience with Hamiltonian methods for solving these? Because in principle, they look really nice. If you've got gradient information, use it. Our experience in practice has been tricky. So I just wondered, what's your experience on those?
So I haven't used Hamiltonian Monte Carlo methods myself, I have to say. So in the community that I'm in, we're typically interested in cases where the unknown U is very high dimensional. So we would typically use things which are dimension independent. So Hamiltonian Monte Carlo, so it has a better, so it's not really robust with respect to the dimension. So it has a better dimension dependence than, say, just random walk or something like that. But we would typically use something like preconditioned Crank-Nicolson, where you can show that it's, other than that, I don't have that much experience with Hamiltonian Monte Carlo.
So the comment about discrepancies, where the approach was to look at something orthogonal to the gradient, isn't one of the issues that in practice the discrepancy is in fact not conveniently sort of orthogonal in that fashion, and that's actually what impacts how it's one of the many reasons why sort of handling discrepancy with something more flexible than that actually is important for you to do calibration in the right way. So I guess to summarize my question is it reasonable to assume something that quite that strong about discrepancy?
So essentially what this means is that, so if you look at this equation here, right, so y, you've got the g of u here already, so everything that's kind of captured by g is already in here. So the eta 2, you want to have everything that isn't captured by g, and then this here, that you define eta 2 to be orthogonal to the gradient, that is, in a mathematical way, that is exactly saying that the eta 2 captures everything that the g doesn't. So it is quite a strong model. So I mean, one of the benefits is that you do actually get an identifiable problem.
Right.
exactly because you can really distinguish the contribution from what's already in G. But yeah, I mean, there's no guarantee that that the model discrepancy is actually.
Right.
I don't know about that.
So mathematically and computationally, that's a really excellent way to do things. In practice, especially I work with climate scientists quite a bit, and a lot of the problems that they have, the discrepancy doesn't quite parcel out in that fashion, and that actually it makes a big difference to how you end up calibrating in climate analysis.
Okay, maybe we can talk more about that later.
Hi. So can I just ask you just a small question on that slide, in fact?
Yeah.
So you say that U star is defined by minimizing a loss function. Is that defined by I was trying to get my head around this. Is that defined on the loss function where you've already composed the constraint that the model discrepancy is orthogonal to the tangent?
No.
No. So
No. So
if you did that, would it actually make a difference? I was trying thinking about this while you were talking. I mean,
yeah. No. So it's just you just look at the data y, and you look at g of u, and you look at that difference in a certain norm, and then you just choose the u star that minimizes the difference between y and g of u in that norm.
But if you imposed the constraint first, that it had to be, would that be a different? I mean, which is what the model you're actually trying to live in? Would that give you a different minimization? It seems to me if it would, that seems to be the right way to do it. And I couldn't work out from listening to you whether that's hugely more difficult or whether it's the same.
Yeah. So the way it's done, the way it's derived in this paper, is definitely going this way.
However,
yeah, I have to think about it.
Just while Rich is setting up.
Yeah, I was going to follow up on both of those questions. I mean, one of the things that makes model discrepancy so hard is if you start getting regimes where you're trying to extrapolate, which is what we're trying to do on time-dependent problems, the only thing that carries you into that regime is the physics or the biology or whatever the process. And I haven't looked at, I'm going to go look at the Plumlee paper, but some of the other methods work very well when you're doing interpolatory predictions, but extrapolating, you almost have to go into the model itself and figure out the parts that you trust and the parts that you don't, and start putting some of these functions into the parts that you don't. And when I tell my students that's research opportunities, but it's also one of the things that's really hard, and I think was kind of being hinted at this last question of what's happening on some of these general theories of, because when you try and extrapolate, you have to get the physics right.
Mm-hmm. Okay.
Okay, let's thank Aretha again for being on.